Alright, let's take another shot at this. Number 64. We only had to do part A. Part A wanted to know how much current is going through the 6-volt battery and the 9-volt battery when that switch up there was closed. I didn't even draw the switch in because it's staying closed for this problem. I'm going to call this voltage 6. I'm going to call this guy over here voltage 9. I'm going to keep my naming really simple. This is resistor 2. This is resistor 4. This is resistor 5. This coming out of this battery is going to be current 6. And when it hits this junction, we're going to say that some of it goes this way. We'll call that current 5 because that's what it hits first. And the current coming down here, which we'll call current 9. And of course, back down here, current 9 and current 5. Current 5 both rejoin back up to become current 6 again. We'll call this left-hand side loop 1. We'll call this right-hand side loop 2. We'll go clockwise just to stay consistent. First of all, I begin with a junction rule. I will focus on this junction. If I did the statement for down here, it would be the same thing. Up here, we've got I6 becomes I5 and I9. Current 6 is equal to current 5 plus current 9. If instead I were to look at this one, I would have had a statement of current 9 plus current 5 equals current 6, which is just the reverse of that. So we don't need that. Now, the loops are where things get complicated. In loop 1, I like to start right before the battery. I'm going in the normal direction for a battery, so that means I'm increasing my potential. So that means voltage 6 is positive. Then I come around this way, and I hit this battery, but I'm going down the battery, so that means voltage 9 is negative. Then I get to this resistor, and my voltage drop across that resistor, it is a voltage drop because I'm going in the direction of my current, is I9 times R4. And then lastly, I come over here, my current's going in the normal direction. I'm going with the current, so that means I'm going downstream, so that means I subtract that one too. This is going to be I6 times R2. This whole thing is equal to 0. Then for loop 2, I'm going to give myself a little bit of space there to play with that one in a minute. Loop 2, starting just before the 9-volt battery, I am going up the battery, so that is a positive voltage. Then I come around here to the side. I'm going with my guessed current going downstream, so that means it's a subtraction of current 5 times R5 for my consumed voltage. Now when I come this way, I'm going upstream. Okay, I said current 9 went down. I'm going the opposite direction. That's like climbing up the slide. So that's going to be plus I9 times R4. Okay, and that finishes me off. Now, you may notice that this one has a negative I9 times R4, and this one has a positive I9 times R4. If we add these two equations up, life will become a bit easier. So we add the two equations. I have V6, which has nothing to cancel it. I have a negative V9 and a positive V9, so they cancel each other out. Then I have that negative I9R4 and that positive I9R4, so they cancel each other out. I have this guy here, negative I5 times R5, and a negative I6 times R2. All that junk is equal to 0. If you take a look at this real quick, this is a third loop. This is loop 3. Because if we went around the outside edge, I would first go up in voltage by 6 volts, then I would be going down by I5R5. Then as I come over here, I'd be going down by I6 times R2. So these were the 3 loops. I like this one. It's only got 2 unknown variables. Basically, I want to come back up here. If we get everybody in terms of I6, then we can get in a statement that solves for I6. So I want to solve one of them for I5, which is going to be this one, and I would like to solve one of them for I9 in terms of I6, which is going to be this top one. So I am not going to use this one here in the middle again. So I want to find loop 1. I would like to solve for I9. So I'm going to take my voltage over to the other side, so that I end up with actually I'm going to take I9 R4 to the other side. I9 times R4, I'm going to divide everything by R4, so I'm just going to jump to it, is all this other stuff, V6 minus V9 minus I6 times R2, all divided by R4. Okay. That means that I have one term which is a negative I6. That's my variable of interest, the thing that I'm trying to solve this equation for, times R2 over R4. That's a real simple ratio. And then I've got, to that I'm going to add V6 minus V9 over R4, which is just a number. So I think I'm going to substitute these ones in here. That's negative I6 times 1/2. That's of course going to be 2 over 4, plus 6 volts minus 9 volts. That's negative 3 volts divided by 4 ohms is negative 3/4. Negative 3/4 of an amp is my statement for I9. Then down here I'm going to solve for I5, so I can get rid of the I5 in that equation. Take that over to the other side so it becomes positive. So I5 is equal to these other things, V6 minus I6 times R2 divided by the R5. Let's isolate out my variable. I end up with I6, which is negative, times R2 over R5 plus V6 divided by R5. Substitute in some numbers in there. I've got I6 times 2/5, no units on that because that is 2 ohms over 5 ohms, plus 6 volts divided by 5 volts. I'm just going to call it 6/5 at the moment. In a second I'll turn everything into decimals. 6/5 of an amp. Alright, I'm going to just move down here. I'm going to rewrite my statement for the junction loop law. I6 equals I5 plus I9. Now I'm going to substitute in those other values. I5 is this one, which is I6, or let's say 2/5 I6 plus 6/5 of an amp. That is not a variable, that is a unit. Then I'm going to add I9, which is up here, which is negative 1/2 I6 minus 3/4 of an amp. Let's convert all this stuff into decimals. 2/5 is 0.4. 6/5 is 1.2 amps. Of course, what I'm doing is I'm making this a denominator of 10, so I'm doubling that, so it's 1.2 minus 0.5 times my unknown variable I6 minus 0.75 amps. So I6 is equal to, let's hold our horses here for a second. I think I made a mistake somewhere. I'm just double checking. 0.4 0.4 from this one and 1/2 from that one. I've misplaced a negative someplace. I lost the negative going from there to there. I knew it didn't add up to be 0.1. So that's negative I6. So this is a negative I6. So this is negative 0.4. Okay, so negative 0.4 I6 and negative 0.5 I6 is negative 0.9 I6. 1.2 amps minus, nope, plus, wait, minus or plus? That looks like a negative up there. That was a negative 3. Yep, looks like negative. Something's not jiving with what I had before. Okay, my 1.2 is supposed to be negative. Where's my 6/5? I5, my, just double checking that things are working out okay here. Something slightly wrong. I'm just trying to figure out what's wrong. That's funny. My 0.4 was positive last time I did this. Oh, my 0.4 is positive here. Oh no, I added the negative in. Negative 2/5. The 6/5 is 6 volts divided by 5 ohms, so that's fine. So that was positive. That's negative. That's negative. We'll keep going with it. See where it leads us. 1.2 amps minus 0.75 amps. 1.2 amps minus 0.75 amps is 0.45 amps. Positive 0.45 amps. Now when I add this over here, okay, we're okay. I add this to this side, so we end up with 1.9 I6 equals 0.45 amps. That's definitely not what I had last time. So I6 is equal to 0.45 divided by 1.9, which is 0.24. 0.24 amps. Now, if that is correct, then we should be able to go to a statement that has the two in relationship to each other nice and simply, which is up here. I9 is equal to these guys. So I'm going to plug that in over here. I9 equals negative I6, which is 0.24 amps, times 1/2 minus 3/4 of an amp. So 0.12 combined with 0.75, and we end up with 0.87. I9, the current going through 9 is negative 0.87 amps. Alright, so current going through my 6-volt battery is a positive 0.24 amps. My current going through my 9-volt battery is a negative 8.7 amps. What that means is we chose to call it downward. It's really going upward. So that's actually not a very good statement. My current going through my as a matter of fact, I'm going to add a direction here. So I'm going to say that it is going up in the circuit. This one over here is 0.87 amps going down in the circuit. All right, and I believe that is the end of it.